In the previous video, we have studied the introduction of imperfections in solids. Imperfections in solids, I have told you that they are also called as defects. What are defects? Defects are nothing but the imperfections in the solids or in the crystal lattice, the imperfections that we see in the arrangement of constituent particles is called as defects. Now in defects, I've already again told you that in any solids you cannot say that any solid is free from defects. You cannot have a perfect crystalline solid. Therefore, there are two main types of defects which we call as point defects and line defects. Which are the two main types of defects? Point defects and line defects. I have explained this, that point defects are the defects that you see around a point or an atom or ion. So point defect means around a particular atom, one particular atom in the arrangement. If suppose this is the arrangement, around a particular point or an atom, there is some defect seen. That is point defect. Whereas line defects means the irregularities. Irregularities means the imperfections. Irregularities means change from the regular arrangement. From the regular arrangement, if you see some changes, you call it as irregularity. Irregularities in the entire row of the solid or crystal system is called as line defects. Now I have told you that again we are going to study mainly about an important type of defect called as point defects, where point defects are further classified as stoichiometric defects, non-stoichiometric defects and impurity defects. What is that? Point defects are further classified as stoichiometric defects, stoichiometric defects, non-stoichiometric defects, and impurity defects. So these are the three important types of defects, out of which now let us discuss first about stoichiometric defects. Again, I have told you stoichiometric defects are those in which there is no change in stoichiometry or that particular defect does not disturb the stoichiometry here, whereas non-stoichiometric defects means these defects will affect the stoichiometry of the solid. Impurity defect, due to presence of the impurity, you can see the defect. And whenever you write the definitions, please do not use common language and write the definitions. There is a particular way of presenting your answers, and I hope that you will follow the same method while delivering your answers in your examinations. First, let us see stoichiometric defects. Stoichiometric defects. First, listen to the class and then do note down the points. Otherwise, what I see is you people just note the way I explain it to you. See, I'm trying to simplify the concept to you and explain, and please do write the note properly in a formal way, not just like how I explain it to you. Okay? Now, stoichiometric defects, and please do refer your NCERT book rather than referring Google or any other, because ultimately the answer key will be from your NCERT book itself. Stoichiometric defects, these defects does not disturb the stoichiometry of solids. This will be the first point which you will be noting. What is it? These defects does not disturb the stoichiometry of the solids. Okay, since it does not disturb the stoichiometry of the solids, there is one more, there are other names for stoichiometric defects which are called as intrinsic defects or thermodynamic defects. What are they called as? They are also called as, that means you have to write it, these are also called as intrinsic. Intrinsic usually used to denote the pure form, intrinsic or thermodynamic defects. Thermodynamic defects. On heating also you can see a few of these defects, and hence they are called as thermodynamic defects or intrinsic defects. Hope it is clear. Now, in this, especially in stoichiometric defect, we have two more types of defects which are called as vacancy defect and interstitial defect. Two types of defects are vacancy defect and interstitial defects. Vacancy defects and interstitial defects. Now let me explain you what is a vacancy defect. Now you observe, first I am going to explain it to you, understand. Now if this is an arrangement of solid, if this is a crystal system, then the arrangement of solid, if suppose the constituent particles are arranged close to one another, just to show how the defect takes place, let us show the particles away from each other, say it's compactly packed. Now if suppose there is missing of any one of the atom here, if there is missing of any one of the atom, what does it create? It creates a vacancy here, isn't it? A vacancy is created. This such a defect where any one or more atom is missing, atom or atoms are missing from the solids or in the solids, we call the defect as vacancy defect, which creates a vacancy site. SITE. It creates a vacancy site. The defect in which there is missing of one or more atoms from the solid system, which creates a vacancy, is called as vacancy defect. If suppose there is vacancy, what may happen to the density? Whether density increases or density decreases? Obviously, see here, the expected density was more, isn't it? If there was one more atom, the density would have been more. But now there is missing of an atom itself is missing from there, and it has created a vacancy, a hole there. A vacancy is created. So this particular region is missing an atom. Now what happens to density in this? Density decreases. Density decreases in vacancy defect. So please make a note of what is vacancy defect, as I have told you, and then what happens to the density of the substance. Usually this takes place, vacancy defect takes place when there is heating of any solid. When the heating of solid takes place, then there's possibility that any one atom may escape from its normal site and create vacancy there, which leads to vacancy defect. Now let us see what is interstitial defect. Interstitial defect means, see, from the normal position. Now this is a normal position, isn't it? In this I'm going to explain. Next I'll explain again. See, in this, these spaces you can see here, apart from the normal, this is a regular arrangement now. This is a regular arrangement. Apart from this regular arrangement, all these spaces are called as interstitial sites. Okay, interstitial site means the site or region other than the normal site. It's called as interstitial site. In interstitial defect, what happens is, see, if this is the arrangement, this is a normal arrangement expected, isn't it? But here what happens is, any one of the atoms, it might be dislocated from that position, and that atom may occupy some interstitial site here. The same atom, I'm just drawing it separately because it is occupied some interstitial site. What has happened? It has created a vacancy here, isn't it? That means here this is a type of defect in which an atom or ion dislocates from the normal site and occupies interstitial site, and this defect is called as interstitial defect. Hope you're getting it. That means an atom which should have been in normal site, this is a normal order, it does not follow that order. Instead, that atom comes and occupies one more space which is not normal. It is abnormal site. Don't write abnormal site. It's called as interstitial site. So let us define interstitial defect. The defect in which the atom gets dislocated and occupies the interstitial site. Interstitial site is called as interstitial defect. Now you have understood what interstitial means. Interstitial means not the normal arrangement. Different arrangement than the normal one is called as interstitial defect. Now what may happen to the density, whether density increases or decreases here? Yes, the atom from here comes and occupies here. So in general what happens is, interstitial defects, you see that density increases. Because you just imagine from the whole crystal system, now if we consider a part of it from somewhere from the normal position in the interstitial position, if the atom comes and occupies, what happens to that density, that particular space? If you calculate density will be more. Therefore, density increases for interstitial defect. If this is clear, we will proceed further, where this stoichiometric defects and interstitial defects can be explained in non-ionic solids. What is it? Vacancy defect and interstitial defect can be explained in non-ionic solids which are not ionic. In that you can easily explain, or you can well explain, vacancy defect and stoichiometric defect. Okay, what about ionic solids then? We will see about ionic solids, whereas this vacancy and interstitial defect can be explained in which one? In non-ionic solids. Under stoichiometric defects itself, we are continuing now. We will study the defects in ionic solids. We will study the defects in ionic solids now. Remember one more thing, that interstitial defect is also called as dislocation defect. Okay, just make a note there that interstitial defect is also called as dislocation defect. Now, in case of ionic solids, in ionic solids, we see stoichiometric defects in ionic solids. What are those defects that we see in ionic solids? The defects which we see in ionic solids are Frenkel defect and Schottky defect. SCHOTTKY, Schottky defect. Very important, as most commonly they do ask the difference between Frenkel defect and Schottky defect. Otherwise, they ask you to define Schottky defect and give an example, define Frenkel defect, give an example. Otherwise, the change in their density is asked. So do concentrate. What is Frenkel defect now? First, let us study about Frenkel defect. Then we will see the difference between them. Very easy. Frenkel defect. You know, in this defect, usually what happens is, this happens when the smaller ion is the cation. Smaller ion is the cation. This one. Now the larger ion is anion. In the textbook they have given you both of same size, but in fact Frenkel defect takes place when the cation is of smaller size and anion is of larger size. Do remember this. Okay, so first point you will write, this defect is observed when cations means positively charged ions, are smaller in size than anions. Anions means negatively charged ions. So anions will be larger in size, cations will be smaller in size. Now here what happens? That is a question. In Frenkel defect what happens is, an ion, smaller ion usually gets dislocated. Smaller ions, say this is a smaller ion now, positively charged ion, that gets dislocated from the normal site and it occupies the interstitial site. Now here the ion which was present, I am just showing it to you as blue colored ion here, which means the ion from normal site gets dislocated to the interstitial site. This is Frenkel defect. Now here what has happened? The smaller cation has dislocated from normal site to interstitial site. Now here what happens, you know, in this site which type of defect do you see? Here you see vacancy defect, and in the new site you see interstitial defect, isn't it? You find both vacancy defect as well as interstitial defect here. What is it? An atom from normal site gets dislocated to the normal that is to the new interstitial site. So you will write Frenkel defect is the one which is observed when cations are smaller in size than anions and cations are dislocated from normal site and occupy interstitial site Frenkel defect is also called as dislocation defect. Hope you are getting it. This is Frenkel defect where cation is smaller in size and anion is larger in size. Cations are smaller in size, anions are larger in size here. One more thing, what you have to see here is that the point that has to be noted is it does not change density. This defect does not change the density of the solid. Density remains same. Very important point. Now the example for the ionic solids that shows this Frenkel defect. Example, see, what is the condition? Cations must be smaller, anions must be larger. So example for the solids that shows this type of Frenkel defect is silver chloride AgCl, zinc sulfide ZnS, AgBr silver bromide. These are the main examples for etc. Are examples for the solids that shows Frenkel defect. So this is about Frenkel defect. Hope you have followed it. Very important. Do understand so that next defect, if you learn, you can easily differentiate these two defects. Next we will see what is Schottky defect. In Schottky defect, again we see this particular defect in ionic solids only. Schottky defects. In this defect is observed when cations and anions are of similar sizes, are almost of similar sizes, then we see Schottky defect. Here missing of equal number of cations and equal number of anions takes place. This defect is observed when cations and anions have almost similar sizes. Similar sizes. So here you don't have that cation is smaller, anion is larger. Both have almost similar sizes. And in this particular defect, equal number of cations and anions will be missing. And anions will be missing. Now let us see how it looks like. See, if you consider a solid, then the normal arrangement expected is plus minus, isn't it? This way. So if there is plus here, then next comes minus, plus, minus. You know, alternate positive and negative charges. Hope you know how to write. Here if it is minus, then I have to write plus here. If it is plus, minus, minus, plus, minus, plus. This is how we write. Now here what happens is, in this case, where we see Schottky defect, equal number of anions and cations are missing. If suppose there is missing of one positive charge, it creates a defect here, isn't it? There is missing of one positive charge from the side. There will be missing of one negative charge also then. One equal number of cations and anions are missing. It need not be only one cation and one anion missing. There can be possibility that one more positive charge, if it is missing, somewhere in the crystal lattice, one more negative charge will be missing. So that means equal number of cations and anions are missing from the or in the solids, and which leads to a defect called as Schottky defect. So here cations and anions are of almost similar sizes. Now what happens to density is the question. What happens to density? Here you can see cations are missing, equal number of cations and anions are missing. Whereas in the previous one, from a particular site, the atom got dislocated at some particular site. So density remains same there in case of Frenkel defect, in case of ionic solids. Now here in case of Schottky defect, what happens? The density decreases. Next point is density of the solid decreases. Density of the solid decreases. This is one more point to be noted. Now next we will see the example for the solids that shows this particular Schottky defect. Example, here what is the condition? The atoms that show or the solids that show Schottky defect will have almost similar sizes. Example, sodium chloride, silver bromide, AgBr. What you can see is again potassium chloride, KCl, cesium chloride, CsCl, etc. These are examples for the ones which shows Schottky defect. One notable point is that Schottky defect as well as Frenkel defect both are shown by silver bromide. AgBr is a common example for Schottky and Frenkel defect. I repeat the point, this particular point, that AgBr shows both Schottky defect, silver bromide shows both Schottky as well as Frenkel defect. Why I am highlighting this statement is because they will ask you, give an example for a solid which shows both Schottky and Frenkel defect, then your answer must be silver bromide, and that is why it's very important to be known. Hope it is clear. Next we will move on to next type of defect. Now so far what you have studied is stoichiometric defect, and in that Frenkel defect and Schottky defect. If suppose they ask you to differentiate between Frenkel defect and Schottky defect, how do you differentiate? Frenkel defect takes place due to dislocation of the atom, that is smaller cation from normal site to interstitial site. In case of Schottky defect, you will be writing equal number of cations and anions are missing in the solids. Then under Frenkel defect, you will write density remains same or density does not change. Whereas in Schottky defect, density of the solid decreases. And example for Frenkel defect, you know, example for Schottky